We're looking at differential equations for this week, same as last week. And remember that all the differential equations we've been looking at have been reduced to first order. First order. And the nice thing about first order is that it's all about slopes. As soon as you say the first derivative equals, then what you're talking about is some estimate of slope on a graph. dy dx, dy dt, whatever. And we can rearrange that because dy dt can be approximated by talk about a change in y over change in t, and we can bring the change in t on the other side, and we get this nice little relationship that says, if I know my slope and I take a small step in delta t, I can tell you how much my y changes by. I can predict, I can simulate what the change in my temperature, in my velocity, in my whatever it is, if I know the rate of change and I'm willing to take a small step of time, delta t. That's a pretty powerful insight, quite frankly, that we can go from first derivatives, interpret them as slopes, and say, okay, from some starting point, I can find the slope, follow the slope, find the slope again, follow that slope, find the slope again, follow that slope, and generate some approximation of what a complicated system would do if we know the rule, which is the differential equation. So we built some solvers last time, and what we're going to do this time is extend that a bit. Last class, we had scalar values. We had y, dy dt, and that's all we had. Now, what we're going to have is w, which will be a vector of two things, or four things. It doesn't really matter. It could be n variables. But we should be able to extend our code so it handles this general case. The math underneath the hood is identical, except we're going to basically add vector things. Everywhere we had a y before, we're going to change it to a vector. We'll see how that plays out. But we're going to do it in the context of something that we all know and love at this point in our careers, which is the spring mass system. If we look at the spring mass, it has the F of the spring, and we're not even going to consider friction, so we'll keep it really simple. The force exerted by the spring is negative kx. If I stretch a spring out, and as soon as we say that, well, we have the sum of the forces as mass times acceleration. And that means, let's bring this over here, mass times x double prime is going to equal our spring force. Or x double prime is going to equal 1 over m times minus kx, or I can rearrange that a little bit, minus kx. There we go. Now we have to convert this, if we want to take advantage of all this funky techniques about first order derivatives, we have to convert this second derivative here into first derivatives only. No second derivatives allowed. The system we're going to use for that is the same one we've used before. We're going to define new variables. The first variable is going to be the same as the variable in our question. W1 is going to be x. And then our new variable, our second new variable, is going to be W2, and it's just going to be the derivative of x. So it's going to be x prime. So that's the first step in creating a first order system. We make two new variables. To make the rest of the system, we create it by looking at the derivative of each of those and say, hey, what would I get if I differentiated W1? Well, I'd get the derivative of what W1 is, which is x. What's that going to equal altogether? W2. Wasn't quite altogether, but we'll work with it. So the derivative of my first new variable, W1, is x prime, but x prime is the actual W2. So the derivative of the first one is the second one. The derivative of the second variable, well, the second variable is already x prime. We're going to take the derivative again, and we're going to get x double prime. This is where our F equals ma thing comes in. We already said that x double prime for a spring system would be minus k over mx, or minus k over m W1. So our original differential equation, which was x double prime equals, is going right in here. Watch YouTube. All right. So that's what we've got. Next thing, better before going to the code, is to say, what do we expect? So if this is our x, and this is our x prime, if we start at x equals 4, sorry, the initial position is 4, and initial velocity is 0, What are we talking about? We're talking about a spring system here. We've displaced it so the natural position is here. We've stretched it out so the spring is extended to 4. What do we expect this graph to look like here? So we expect something like this, right? The spring is going to oscillate back and forth. On our graph of t with x being vertically laid out now, we're going to see it as vertical oscillations on our graph. The velocity is going to do the same thing, maybe to a different extent, but just basically out of sync. Because when is the thing moving fastest? The mass is going to be moving fastest when it goes through 0. That's when it's got all kinetic, no potential energy. Then it's going to go and slow down when it gets all potential, no kinetic. There's a nice little energy argument you can make around that. But we're going to get a couple of trig function curves, sine curves, cos curves of some species here.